Hello everyone, and welcome to part 2 of the demonstration for the NIMS Step Block, which is a project in the Machining 220 course at Laney College. In the first demonstration, we roughed out the part. So we machined it to its overall dimensions, height, width, and depth, and then we came in and machined these steps and the slot, and we even pre-drilled this hole. In this video, we're going to finish all of the planar surfaces. So that's all of the outside surfaces, the steps, and the slot. In the third and final part, we're going to finish all of the holes on the top of the part. Whenever we're machining a part, we always have to ask ourselves, what is the appropriate sequence of operations? Which surfaces should be finished first, second, third, etc. Now, the print doesn't tell us how to machine the part. That is the prerogative of the machinist. But it does tell us what the final inspection criteria are. And those final inspection criteria very often specify a priority of surfaces, and that in turn suggests a sequence of operations. In the case of the NIMS Step Block, if we look at all of these GD and T callouts in the feature control frames, we can see that there are a number of places where we have datum references. In some places there's only one or maybe two datum references, and in other places there are even 3 datum references, a true datum reference framework. So if we take all of these GD and T callouts and retrace the logic, we'll find that all of these GD and T controls ultimately reference datum A down here. These two surfaces are parallel to datum A. This surface is perpendicular to datum A. This surface is parallel to D, which is perpendicular to A. This surface right here is perpendicular to A and to B. And then all of the tolerance of position controls are called out to A, C, and D, where A is the primary datum, C is the secondary, and D is the tertiary. So datum A, down here on the bottom of the part, is our most important datum. Therefore, datum feature A, meaning the actual surface on the bottom of the part, is our most important surface. So it makes total sense that we should finish that one first and then machine everything else relative to that surface. But what about the second and third surfaces? Well, for those, we're going to take our cue from the datum reference frameworks for the tolerance of position controls. Okay? A, C, and D. Again, it makes sense to finish these surfaces in their order of priority according to the datum reference framework. So we'll finish datum feature C, which is the left side of the part, second, and then we'll finish datum feature D, which is the front of the part, in the front view here, third. As for the fourth and fifth surfaces, we're going to finish the opposite sides from C and D. That way, 5 out of the basic 6 sides of this part, which is essentially a rectangular prism like a cube, will be complete. And all we need to do at that point is focus on the top of the part, finishing the steps, the slot, and then putting the holes in. So let's get all of that done first, and then we can come back and talk about what we're going to do to the top of the part. The strategy that we're going to employ here to finish all of these outside surfaces is going to be exactly the same as what we did for the angle plate project in Machining 210. We're going to be using parallels to support the part and provide some kind of a rough alignment. But the actual final alignment of the part to ensure squareness is going to be achieved with an indicator and an indicall. And the material removal will be achieved using a fly cutter and an R8 collet. When you're selecting the size of your parallels, remember that there are sort of 2 things that you're looking out for. One is that you want to be able to hold as much of the part as you can while still having access to all of the surfaces that you need to machine. The second thing is that you need to allow for clearance for your precision measuring instruments. The largest distance that we have to measure on this part is going to require a 2 to 3 inch micrometer. And for this particular micrometer that I'm going to use, these 1-inch parallels are sort of the minimum size that we can use while still getting this thing underneath the part so that we can measure over those surfaces. So this is what I'm going to use. I clean everything up real nicely. Parallels get cleaned, just quickly wiped off with a hand. Okay. Now, we're going to put the part in like this with those 2 little sort of small surfaces down on the parallels like this. We're not worried about the orientation of the part too much because none of these surfaces are finished yet. We're about to start establishing our finished surfaces. So as long as the part's not cocked out too much, we don't really care that much about the orientation. As long as this orientation allows us to remove enough material to finish all of the surfaces, then we're okay. By the way, if you haven't done so already, make sure that you deburr all of the edges on the top of the part that you made with the roughing end mill, okay? That's really going to affect the way that this sits down on the parallels. Okay, tighten that down. Okay, collet goes in. Get that started. Followed closely by the fly cutter. Pull the drawbar in. Lock that down. Because these cutters only have one cutting edge, I always do a dynamic touch-off with these. So let me go ahead and start this thing up. Okay, I'm going to go ahead and position this about center of the part so we can take everything in one go. Raise the knee a little. Actually, let me go ahead and bring this a little bit closer with the quill. There we go, just so I'm not moving the knee quite so much. All right. Raise the knee right there. Good touch off. Zero it. I'm going to take 5 thousandths just to clean it up. Adjust my feed rate by moving the part away from the cutter and engage the cut. All right, there we go. With the fly cutters, we only usually cut on this forward stroke, I guess. We don't let it cut on the back, just because we get a slightly better surface that way. You know, really only taking a minimal cut here. 5 thousandths was all it took, so that's all I'm going to give it. There's no need to take any, you know, some minimum distance here, right? It's just to clean up the surface. All right. Go ahead and take that out. That looks really, really, really nice. Okay? If your surface doesn't look good, then it's probably because your cutter is dull and you really need to sharpen this. I mean, if this cutting edge is dull at all, it's going to leave a really crappy finish. Okay, Datum feature A is finished. Now we're going to align that vertically and finish Datum feature C so that it's perpendicular to A. Go ahead and lift this up, lower the knee. Okay folks, I'm actually going to take these parallels out for just a moment. And I'm going to put these smaller parallels in. And then I'm just going to install the part like this, so that Datum feature A is exposed on the side so that I can actually go in and indicate it. Now we're not holding on to a lot of the part, but that's okay for two reasons. One, because we're going to be taking a very, very small cut on the top surface here. And also because we actually want to create a little bit of a pivot point so that when we're making our adjustments with the indicator, it follows a sort of predictable path. Okay. Install the indicol like so. That looks perfect. Put it in low gear so it doesn't move around on me. Now I'm actually going to rough align the surface using the quill, okay? But I'm not going to trust the quill for final alignment. The knee is a much, much more accurate path of travel, which does not take into account any kind of tramming errors that we may have in this setup. But the knee is kind of cumbersome to move, and so just for convenience's sake, I'm going to rough align it with the quill and then go in just for the final adjustments and final inspection with the knee. So let me go ahead and zero this out right there, then move it down to the bottom of the part, and it looks like we're getting about 4.5 thousandths in the minus direction, okay? That means that the bottom of the part is further this way, further away from the indicator than the top of the part is. So we could move the bottom of the part out towards the camera this way, but since the bottom of the part is where the pivot point is, we're going to have to make all of our adjustments on the top here. So actually I'm going to push the top of the part this way, away from the camera. And I'm going to do it with a soft-faced mallet or a dead blow hammer. Okay, here we go. Okay, let's re-zero that and see where we are. Much, much closer. So it looks like we're about 1/2 thousandths, maybe 1 thousandths out. Still in the same direction, so I still need to kick this out a little bit more in this direction. Maybe right there. Okay, 0. About 1/2 thousandths in the minus direction. Okay. Let's give it another little. Re-zero it. Let's try again. Yep, pretty much 0. Okay, definitely time to go in with the knee now. And that says, yeah, just a little bit under 0, maybe 1/2 thousand, or sorry, 1/2 graduation under 0, so maybe 1/4 thousandths. Let's move back to the top and see what it says. So it moved just a little bit over the 0, okay? So I'm going to go ahead and just kick it in just a little bit. Just a little bit. I'm going to tighten down on the vise. And now we're going to recheck it one last time. Okay, it went just a tiny little bit over 0. Go back to the top and double check it. Okay, nearly perfect, okay? And I'm already tight on the vise, so that's it. All right, indicator and intercol come off. Okay, raise the part up so it's relatively close to the fly cutter. Back into high gear there. Okay, kind of get it close with the quill. Right there is good. Turn it on. Slowly inch up with the knee until you just touch off on the surface. Right there. Back off. Adjust your 0. Go in 5 thousandths. Engage the cut. All right. That's it. Second surface done. Okay. Very, very, very nice finish there. Okay, so Datum feature C is finished, and now what we need to do is go in and finish Datum feature D, which is the front surface of the part if you're looking at the front view. So to finish this surface here, again, we want to leave Datum feature A exposed so that we can align it up and down, but we do want some way of getting ourselves relatively perpendicular to Datum feature C as well. So what I'm going to do is flip the part around like this. Now Datum feature A is exposed on the left side of the part. Datum feature C will be up against the fixed jaw of the vise, which is a pretty decent fixturing surface. We know it's relatively straight up and down. And Datum feature D is exposed for our cut. Okay, let's zero this out. Okay. Let's see what we have with the quill. That's not that bad. Okay, so it's, let's see, plus 1.5. Okay, so we need to bring the top of the part out. Re-zero it, like so. Check it again. Okay, it's pretty close. All right, let's try that. Zero, zero, okay. Okay, I'm going to tighten the vise just a little bit, re-zero it, and then check it with the knee. Okay, so that's about 1 graduation, so 1/2 thousandths. Maybe just a little bit more. Something like that. Re-zero. Check it again. Very, very, very good. Okay, let me go ahead and tighten it down fully. And let's do a final check. Excellent. Okay, let's bring the table back up. Let's take a cut going this way this time. Why not? Get that table pretty close. Maybe bump it down a little bit with the quill. Right about there. Okay, put it back into high gear. Turn it on. Gonna readjust the position of the cutter so it's going down the center of the part. Okay, and then I'm gonna bring it up with the knee. So we just touch off. There we go. All right, zero the dial on the knee crank. Give it 5 thousandths, and hopefully it cleans up. And it looks like it is cleaning up beautifully. All right, that's all it takes. Okay, remove the part from the vise. Okay, so now we have 1, 2, 3 surfaces finished, and that makes up our Datum reference framework for our tolerance of position controls. And now all we need to do is go in and finish the sides opposite the two that we just finished. So side opposite C and side opposite D. Those two surfaces need to be parallel to C and D. And so the way that we're going to do that is by hammering the part down onto the parallels. And in order to make sure that the part is truly down on the parallels and we're going to get a parallel surface, we're going to use the shim trick and put shims between the corners of the part and the parallels. And if all of the shims don't move, then we know that the part is truly down on the parallels, and when we machine our surface, we'll get a surface which is parallel to the one down on the parallels. It doesn't matter what size the shims are, as long as they are the same size, and that can be very easily verified with a micrometer. Okay, I'm going to have to switch these parallels out for the bigger ones. These parallels, because I'm going to have to get that micrometer down in there. So side opposite C comes first, just like that. Shims under all 4 corners. Okay. Tighten the vise down. Hammer down on the part. Do the shims move? That one doesn't move. That one doesn't move. That one does move. That one doesn't move. That one is moving a little bit. Okay. Not moving, not moving, not moving, not moving. Perfect. I'm going to move the y-axis over a little bit so I can recenter my tool. Okay. Bring the cutting edge close with the quill, about right there. Turn the spindle on. Make sure your quill is locked. Raise the knee slowly till we just make contact. Right there. Okay, 0 the knee. Let's give it 5 thousandths and just clean it up. Okay, let's take a measurement. Make sure that you're not measuring over top of the shims. Looks good right there. So what is that telling me? That's telling me 2 inches, 519 thousandths. So the final dimension here is going to be 2 inches, 500 thousandths. So 2 inches, 519 minus 2 inches, 500 is 19 thousandths, which is how much we still have to go. And because we're using a fly cutter, I'm going to take that in 2 cuts of about 10 thousandths. Turn it back on. Come back to the start of the cut. All right, go in 10 thousandths from where I am right now. Okay, take that cut. Back to the start of the cut. Remember, we only like to cut going one way with these. Turn it back on. And then another 9 thousandths. That gets us to our total of 19. Let's take a final measurement. And that's telling me 2 inches, 500 thousandths and a half. So definitely within tolerance. All right, remove the part. Okay, we're going to finish the side opposite datum feature D now. Okay, so datum feature D goes down onto the parallels. Because of this step right here, there's no material over top of the parallel on this side, so we only need 3 shims. So one here, one here, and one here. Tighten the vise down. All right, give it a little tappy tap. That shim doesn't move. That shim doesn't move. Does this shim move? Yes, it does. Give it a little tap right here. Doesn't move. Doesn't move. Doesn't move. We're good. All right, folks, you know the tune. Let's do it again. Go ahead and position this to the center of the part, going this way. Bring it a little bit closer with the quill. Okay, turn it on. Raise the knee up just until we touch. Right there. Zero out the dial on the knee crank. Give it 5 thousandths to clean it up. Okay, now we need a 1 to 2 micrometer. Take a measurement across the 2 surfaces. And that's telling me 1 inch, 875 plus 19 and a half. So 1 inch, 894 thousandths and 5 tenths. The final dimension for the depth of the part is going to be 1 inch, 875 thousandths. So we're at 1 inch, 894 and a half, and we want to end up at 1 inch, 875, so 19 and a half thousandths. Makes sense. Okay, so this is basically the same cut that I had to take on the other side. So I'm going to do 2 passes, 1 of 10 and 1 of 9. Here's 10 thousandths. All right, 9 thousandths now. Final cut. Okay, final measurement here just to verify that we got what we wanted. Okay. So that's telling me 1 inch, 875 and a half of a thousandths, which is exactly what I expected, right? Because we're 19 and a half thousandths oversize. I took 19 thousandths, and now we're a half a thousandths over our target. Definitely within the tolerance, so I'm happy with that. Okay, let me go ahead and remove the part now. All right, folks, that's all the outside surfaces done on the part. The only things which remain to be done are all on the top of the part, so steps and slots and holes and such. The first thing that we're going to take care of are these steps right there. And in order to cut those, we're going to use a Carbide End Mill. Yes, this thing is solid tungsten carbide, which means that you can run it very, very fast, and it produces an absolutely gorgeous finish. But it also means that because it's made out of tungsten carbide, it's very, very brittle. And it's actually even worse than something like an insert for an octamill or something like that, because this end mill geometry has a very, very high positive rake angle, okay, here on the cutting edges, which means that right where the cut is happening, the material is very, very thin, almost razor thin. So this is a super brittle material with a very, very weak edge. So it's like a double whammy right here, and these tools are very, very prone to chipping and breaking. Add to that because it's made out of solid carbide, it's ridiculously expensive. In fact, it's kind of questionable whether or not we should be using these on a manual milling machine at all, right? These are really designed to be used with CNC machines, which have very smooth, very reliable movements, whereas on a manual milling machine, everything's a little bit herky-jerky, especially if you're just learning how to use the machine for the first time. Jerky movements and big bites are the things that really spell disaster for this type of tool. But these tools are very common, and we would like you to learn a little bit about them and get some exposure to using them. It's a 1/2-inch tool, and we're going to hold it in a 1/2-inch collet, like so. So the plan is to finish this first step, both the depth and the width of the step, in, let's say, I don't know, looks like maybe 3 or 4 passes. Then do this next step in maybe 2 passes, and then we're going to do the tops of these wings. That's actually the top surface of the part right there, and that's going to establish our overall height. And then we're going to come in and deal with the slot. Although we're going to talk about the slot a little bit more in depth because there's a little bit of a strategy about how you get the size of the slot and its location. And so we'll just talk about that when we get to it. Okay, I'm actually going to put some bigger parallels under there. So these are 1 1/8 of an inch. And the idea here is just that we need to get access to this surface right here. So we at least need, some minimal amount sticking up so that we don't cut into the top of the vise jaws. So that looks like a pretty good fit right there. Okay. Go ahead and lock that down. Give it a couple good whacks. Nice. All right, the 1/2-inch collet goes in. Get that started. A little bit closer than that. Okay, and now our carbide end mill. It is pretty sharp, folks. So it's a good idea to wrap a towel around it. Okay, get that started. Now, really, please, one way that you can keep these things safe is to put something soft underneath them, right? So if they fall, right, they're not going to chip, okay? I mean, we've got these wood protective covers right now over the top of the table. But if you're doing this over top of the vise or something like that, make sure that you put something soft underneath it. I mean, these things will chip even if you just look at them wrong. Okay, let me go ahead and tighten this down. Okay, let's position this for the first cut. Okay, I'm going to get this a little bit closer. We are not going to do a static touch-off with this thing. Definitely not. It's way too brittle, and we could easily chip it if we just touch it to the material without it spinning. I'm going to go ahead and turn it on, adjust the speed. Okay, I'm going to bring the knee up a little bit, nice and slow and steady, just until we touch off. There we go. I'm going to call that my 0 on the knee. Then I'm going to back it off, like so. I'm going to go in 5/1000ths of an inch, and then I'm going to take a cut across. Okay, and then turn it off. Make sure that you don't drag this tool across the surface. Okay, and now we're going to measure the height of that step. All right, bring the micrometer in. All right, what does that say? So that says 750 thousandths of an inch, plus 14 and a half, almost 15. So 764 and a half thousandths. The final dimension is 750 thousandths, 3/4 of an inch, right? So we have 14 and a half thousandths to go. So here's what I'm going to do. I'm going to go ahead and raise the knee 14 and a half thousandths and then take another cut where I just took a cut, and then I'm going to forget about the depth setting. That way, every other pass that I take on this step right there is going to be at that depth, and I'm going to get my 750 thousandths. So here I go. That's 10, 14 and a half right there. Okay, take a cut. All right. Now I'm going to scooch over a little bit, take a cut going the other direction. Okay. I'm going to maybe take another cut going this way. But I'm not touching the side of the step yet. Okay. Now I've pretty much got the depth of the step done. What I'm going to do now is come so that I'm over top of the side of the step, and then I'm going to move in on the x-axis until I just take a tiny little chip off of that side surface. Okay, right there. Okay, I'm going to come off with the tool. Okay, and then I'm going to go ahead and zero out the x-axis on the DRO. I'm going to move over maybe like 5 thousandths or something, some minimal distance, so that I can clean up that whole surface. But I don't want to take too big of a cut right now. I lock the table down, and then I'm going to feed across the surface. Remember, we're trying to do a climb mill. I mean a conventional mill, sorry. Just like that. Okay. Go ahead and stop the spindle. So that looks like it cleaned up very, very nicely. Okay. Let me go ahead and remove all the chips and stuff because we've got to take a measurement now. All right, so I'm going to use a 1 to 2 micrometer for this. And we're going to measure from datum feature C to that shoulder on the step. Okay, what does that say? That's 1 inch, 504 thousandths. So according to the print, the final dimension there is going to be 1 inch, 500 thousandths. So if we're at 1 inch, 504, then we need to take 4 thousandths off of this surface. Now you can see why I didn't really want to take very much material off for our cleanup cut. Okay, I'm going to loosen the table and feed over another 4 thousandths to 9 thousandths right there. Turn on the spindle. And I'm going to actually do a climb cut this time, okay? This is a very, very small cut, okay? So climb cutting is going to be okay here. Nice and stable feed. Okay. Okay, where did we end up with this surface? Okay, 1 inch, 500 thousandths on the money. And it's a really, really nice surface finish too. Okay, let's go ahead and do the same thing with the other step. Okay, dynamic touch off with the knee, nice and slow. Okay, just touched off there. I'm going to call that 0 on the dial on the knee. Let's go 5 thousandths. Okay, give myself a little bit of material to cut here and then feed across the surface. Okay. Okay, let's go in with this 1 to 2 inch micrometer, and that just reaches. Okay. So that's telling me 1 inch 125 plus 16. So 1 inch 141 thousandths. The final dimension is 1 inch 125 thousandths from datum feature A to the bottom of the step. So we have 16 thousandths to go. Again, what I'm going to do is just raise the knee by 16 thousandths, take another cut, and then just forget about the depth. So that's 10, 15, and 16 thousandths right there. Turn it back on. All right, take another cut somewhere like right there. All right, perfect. Now I'm going to go back in so that I'm, over top of the vertical surface, right, the side of the step there. And I'm going to slowly move in on the x-axis until I just take a cut. So right there, and then feed off of the part. So looking at my digital readout, where I just touched off is 500 thousandths of an inch from where my last cut was, from where the last step was, okay? And actually, that's where we're supposed to be. There's supposed to be a difference of 500 thousandths there between the positions of the two steps. I'm going to go ahead and lock this down and take a cut. Okay, let's take a measurement. So that says 1 inch and 8 thousandths. So the final dimension in this direction is 1 inch from datum feature C. So if we're at 1 inch and 8 thousandths, then we have to take 8 thousandths. Now that doesn't really agree with what the digital readout was telling us, but the micrometer doesn't lie, so we'll take 8 thousandths. So I'm going to reset the 0 on the x-axis, and I'm going to move over my 8 thousandths. And right there. Another 2/10 isn't going to hurt us. Turn the spindle on, and I'm going to do another climb cut. Nice and gentle. Okay, Final measurement here. Okay. So 499 thousandths and a half, 0.4995, or something very close to that. So definitely within tolerance there. Okay, moving on, let's not forget about the tops of these two tabs here. That actually forms the overall height of the part, okay? And we're just going to do that with the end mill right now. Dynamic touch off on the top. All right, right there. Okay, zero out the dial on the knee. Let's go 5 thousandths. All right, let's take a cut. And I'm going to zigzag over that first tab right there, and then we'll take a measurement. Perfect. Okay, let's see what we've got here. Okay, lock that down. Okay, so that says 1 inch, 375 thousandths plus 19 and a half. So that's 1 inch, 394 and a half. So the final dimension for that overall height is 1 inch, 375. We're at 1 inch, 394 and a half right now, so we need to take 19 and a half thousandths. So I'm going to go ahead and take that all in one go. So on the knee, I'm going to go 10, 15, 19 thousandths right there. Let's take a cut across those surfaces. Okay, and without moving the depth at all, either on the quill or on the knee, I'm going to come over and I'm going to do the other side. Okay, final measurement here. Lock it down, remove it. And that's telling me 1 inch, 375 and a half. So definitely within tolerance. Okay, it's time to machine the slot. But before we actually get started, let's just talk about this a little bit. Okay folks, before we actually cut anything on this slot, I want to go in and talk about the criteria for the slot, which should inform our strategy for machining it. I'm going to be demonstrating on this extra sort of half-done part that I have lying around. So there are two dimensions which relate to the slot. It has a width, 875 thousandths, and it has a depth. Actually, the depth is not given to us. The distance from datum feature A to the bottom of the slot are given to us, or is given to us, and that's 1 inch. As well as having a size, of course, the slot also has a position, and the positional tolerance is provided here by this tolerance of position control. So this is a GD&T control which applies to the slot. The tolerance is 5 thousandths relative to datums A and B. Well, datum A is the bottom of the part, and datum B is this datum right here. In the video where I talk about inspection, we discussed this special circumstance for datum features where the datum identification symbol is in line with the dimension line, meaning that it's actually not this surface, which is datum B. Actually, this surface is datum D. You can see that there the datum identification symbol is not aligned with any of these dimension lines. It's actually just on the extension line. And so this surface right here is datum D. So you might think to yourself, well, then B and D are redundant. But no, datum B, actually because of its position, means that it is a center plane constructed from this surface and this surface. So then what does it mean for the slot to be positioned within 5 thousandths relative to datums A and B, the bottom of the part and the center plane of the part between datum feature D and its opposite surface? Well, what this is getting at is that this dimension, this length dimension, has a tolerance, 3 decimal places plus or minus 5 thousandths. And then the width of the slot also has a dimensional tolerance, right? That's also 3 decimal places, so plus or minus 5 thousandths. So this means that the center plane of the slot has to be positioned within 5 thousandths of an inch to the center plane of the part. Regardless of what the size is, the actual dimensions end up being, they want that slot to be right smack dab in the center of the part. That's the gist of it. That explains the datum B callout. The datum A callout means that they want the center plane of the slot to be perpendicular to the bottom of the part. They don't want the slot going off at some weird angle. They want the sides of the slot to be straight up and down. Okay, so keeping all of that in mind, let's talk about our strategy for machining this thing. I provide this handout for people to make this particular feature. It's a detailed procedure for finishing the slot. It's very, very, very detailed. I found that for whatever reason, people have difficulty making the slot. I don't really know why, but in any case, let's talk about the strategy here. Finishing the 1-inch dimension relative to datum A is a pretty easy thing to do, right? Just like we did with the steps, all we have to do is take a pass right through the center of the slot, some minimal amount, measure it, adjust the position of the knee, and then just kind of forget about it. Because in the process of cutting the 2 sides of the slot, we're going to be passing over the bottom of the slot several times, and so it's going to come out to wherever we position the end mill with the knee of the milling machine. Easy enough. The next thing that we need to do before we start worrying about the width of the slot is get the slot on center. The first thing we're going to do is find the center of the part. Just like we did when we were roughing out the slot, we're going to use the edge finder and touch off both sides of the part and then find the center. Then we're going to call that 0 with the digital readout. That's going to get us really, really close to center of the part, but it's not going to get us right exactly on the money, okay? And since we actually only have 5 thousandths to deal with here, we need to get a little bit closer than what the edge finder can do for us. So what we're going to do is take a cut on both sides of the slot with the end mill, and we're going to take those cuts at equal distances from the 0 that we set on our digital readout, which should be center of the part according to the edge finder. Then we're going to measure these 2 tabs here and here. And if the 0 that we set with the digital readout and the edge finder was truly the center of the part, and we took cuts at equal distances from that center, then these 2 tabs should measure exactly the same thing. If they don't measure the same thing, we need to offset the position of our center, re-zero the digital readout, and then come in and take another little test cut, equal distances from the center of the slot on both sides of the slot, right? Write down both surfaces. And then recheck it. We have to keep doing this until it measures the same thing on both sides. And then we have truly found our center. Once we've found our center, then we can go through the final step here, which is finishing the width. This raises the question, how are we going to measure the width of the slot? We can't measure this directly with a micrometer because we're trying to measure the inside of the slot between these 2 inside surfaces, but these micrometers only measure outside dimensions. We could use the inside blade measurement of a dial caliper, but this is nowhere near close enough for the tolerances that we have for that width. So that's a no-go. So then some students put their thinking caps on and they think, well, why don't we use a telescoping gauge? Because that's what we use for the inside of holes, right? So why don't we just get that down in there, right? And then we just gotta find its proper orientation, like so, lock it down, right? And then very, very, very gently remove it and then measure over top of those contact points, right? This turns an innie into an outie and we can measure that with a micrometer. The problem with this method, though, is that the telescoping gauges really only work for inside diameters. The way that these work is that you rock them through the hole and they naturally conform to the inside diameter. Like on this hole here, they find the largest value this way and the smallest value this way, and that is the true diameter of that hole. But this phenomenon does not occur when you're measuring across two planar surfaces. Like if I open up the telescoping gauge in this orientation and then I rock it through the planar surface, right? I can be cocked out at a pretty aggressive angle, right? And it's not going to naturally conform to being square to the slot like that, right? There's really no good way to get it right on the money. But this is getting very, very close to being the right answer. We just need to take something that takes this basic principle of turning an innie into an outie, but something that stays square to flat surfaces. And that's where these come in. These are adjustable parallels. These are two wedges which ride in a dovetail slide, and these two surfaces on the outside are very, very, very parallel to each other, no matter what position you set them in. But you can see that because they're on this tapered slideway, that you can actually change the distance across them. You can also lock them in position with this screw right here. This is useful for a number of reasons. As the name adjustable parallel suggests, you can set these to whatever size you want, lock them, and then you've just made like some kind of a setting gauge or a parallel of an exact size that you want. But these are also a really, really good way to measure the inside of slots. All we have to do is install the adjustable parallel, open it up so that it conforms to the inside of the slot, and then we can measure over that directly with a micrometer. So you should really think of these as the equivalent of telescoping gauges, but for measuring slots rather than holes. So the way that we're going to get the final width on this slot is that after we get the slot center, we'll take a measurement over top of the adjustable parallel, and then however much more material we have to take to get to our 875 dimension, we're going to take that equally off of both sides so that we get the right size and we keep the slot center. So if this reads 865, for example, that's 10 thousandths shy of the slot width, and so we're going to take 5 thousandths off of both sides according to the digital readout. Hopefully that makes sense. If it doesn't, hopefully it will in just a moment when I walk through it step by step on the machine. Okay, I'm going to go ahead and take the end mill out and put the drill chuck in with the edge finder and then find the center of the part so that I don't have to do any more tool changes once I've already set the position of this thing. Okay, go ahead and turn this on. Make sure that this edge and this edge are deburred because you don't want to be finding the edge of a burr, okay? You want to be finding the edge of the surface. Bring this down just a little bit like so. Okay, go ahead and bring the part into the edge finder. Right there. Okay, raise that off of the part surface. Zero out the y-axis on the digital readout. Now let's go and do the same thing on the other side. And I'm going to spin this around the other way so that we can see it pop out a little bit better. All right, there we go. Okay, lift that off the part surface, turn it off. So the digital readout is telling us 2.0748. Remember, finding center using this method, you don't have to account for the diameter of the edge finder. Okay, all you have to do is split this number in half and then go to that position. So that's 2.0748 divided by 2 gets us 1 inch 37 thou and 4 tenths. So I'm going to move this to 1 inch 37 thousandths and 4 tenths. Oh. right there, and lock it down. Zero out the digital readout. Okay. And let's go ahead and put the end mill back in there. Okay, so the first thing we're going to do is get the depth of the slot down. Okay, so I'm just going to go ahead and come over here over top of the slot, come down pretty close with the quill, lock it down, turn on the spindle. Okay, and then I'm going to touch off with the knee right there. Okay, call that my 0. I'm going to take a 5/1000 cut right through the center, and I'm going to set the power feed for this. Okay, there we go. Okay, let's go ahead and take a measurement right over top of where we just took our cut. Okay, lock it down, remove it, and that's telling me 1 inch and 15 thousandths. Remember, the final dimension is 1 inch, so we need to go another 15 thousandths. Okay, so I'm going to go ahead and lift the knee 5, 10, 15 thousandths right there, and then I'm just going to forget about it. The depth of the slot will just come in naturally as I'm taking my other cuts. Okay, now we're going to take some cleanup cuts off of both sides of the slot. And I want to know which one of these I'm going to touch off on first, and so I'm going to take a measurement off of both of them. Just see which one of them is smaller. Okay, so this side is smaller, so I'm going to touch off on this side first and take a little cleanup cut, and then I'm going to come over here to the other side and take a cut on this side with exactly the same distance from the center as I took over here. Okay, I'm going to come over here, feed in a little bit, and then I'm going to feed in to the surface here on the back side just until I touch off. And right there. Okay, now feed off. So I'm not going to re-zero the digital readout. I'm just going to look at the number that I have on there. Okay, so I'm going to go ahead and take a cut at 155. So right there. And I'm going to take a cut across that surface. Okay, now I'm going to go to the other side of the slot in the minus direction here on the digital readout and take a cut at 155 on this side, equidistant from the center of the part according to our digital readout. And actually, you know, it looks like this side was significantly larger than this side, so I guess the roughing end mill didn't cut perfectly on center. So I'm going to go ahead and take a roughing cut. So I'll set this to 145 and take a cut, and then come back and take another cut at 155, just so that we're taking about the same amount of material off of both sides, so that you know, we're just going to get a little bit more accurate comparison between the two surfaces. Okay, now let's go into 155. All right, take the cut. Okay, let's take a measurement and compare the two sides. This side says 525 thousandths and 7.5. So 1 inch, 532 thousandths and a half. What about this side? 1 inch, 525 and 8.5. So 1 inch, 533 and a half. So we're about 1 thousandths off. Now that's actually pretty good. Let's talk about how far off we're allowed to be. Here's another handout that I like to give people. This tells you how to determine the center position of the slot based off of the widths of these two tabs. It also tells you how to interpret the difference in size between the two tabs to determine what the actual offset of the center plane of the slot is, okay? Because that has to do with the tolerance of position control. So in short, take the difference between the two tab widths and then divide that by 2, and that's the center plane offset, okay? So that's how far the center plane of the slot is from the center plane of the part. The way that the tolerance of position control works out is that you have 5 thousandths of total tolerance, which in this case works out to 2.5 thousandths in either direction from the true center plane. So your maximum center plane offset is 2.5 thousandths, and if you backtrack through the math, then the maximum permissible difference between your tab widths is 5 thousandths of an inch. So in the example that's shown here, with a hypothetical width of the part of 1 inch 875, if you've got 500 over here and 510 over here, you've got 10 thousandths total difference for a center plane offset of 5 thousandths, and this part does not pass inspection. But if this were 500 and this were 505, then your center plane offset would be 2.5 thousandths, and that would be just enough to pass inspection. I hope that makes sense. The big takeaway here is that when you're measuring the tab widths and trying to determine whether or not your slot is on center, they have to agree within 5 thousandths of an inch, and the closer the better. In our case, the difference between the tab widths is only 1 thousandths of an inch, which means that the center plane offset is only a 1/2 thousandths of an inch. And that is totally within the tolerance. So technically we don't need to do anything to change this center position. But just so that we can go through the exercise so that you can see what you would need to do if you were dramatically offset from the center position and you really needed to adjust this, I'm going to go ahead and adjust the center position to really dial this in. Okay, let me go ahead and move this back to the 0 position. Right there. Okay, so this is the tab, which is 1 thousandths of an inch wider than this one. So we need to adjust the 0 on the digital readout so that we bring the end mill closer to this tab, so it takes more material off of here. The amount that we're going to move over is equal to the center plane offset, right? So if there's a 1 thousandths of an inch difference, the center plane offset is half of that, which is 1/2 thousandths of an inch, and we're going to adjust that in the minus direction on the digital readout. So this direction, right? So let me go ahead and bring that to 0.0005 in the minus direction. Not 0.005, 0.0005. Okay, that's 5/10 of a thousandth of an inch. And actually, it doesn't look like I get 5/10. The most that I get is 4, but that's going to be enough. And I'm going to go ahead and re-zero that. Okay, now the only thing left to do is take another little skim cut off of both sides so that I remove a small amount of material from both surfaces at the same position from the center of the part, based off of our position on the digital readout, but in opposite directions, and then remeasure. So let's do 158. Okay, let's go to the other side and see what we get there. 158 in the minus direction now. Okay, let's take a measurement over here. 525 plus 5.5, so 530 thousandths and a half a thousandths. What about over here? That says 525 plus 5, so 530 thousandths. So now there's only a half of a thousandths of difference between the widths of the two tabs. I mean, you can't really get it much closer than that, folks. Okay, great. So that means that the 0 on the digital readout really is 0 on the part now. So now we know that we can trust it, okay? So now we can move on to dialing in the width of the slot. Okay, I've got the adjustable parallel right here. That fits very nicely inside the slot. Just go ahead and open it up inside the slot so that it's touching both sides. Okay, and then we're going to measure over that with the micrometer. So that's telling us 800 plus 15, almost 16. Let's just call it 16. So 816 thousandths. Okay, remember that the target value is 875 minus 816, which is where we are now, gives us 59 thousandths. Okay? Now, divide that by 2, and we get 29 and a half. Let's just make it an even 29 thousandths, and that's how much we're going to take off of each side equally, so that we get to the final size of the slot, and we also get that slot on center. Okay, so the last two cuts were taken at 158 thousandths from 0. 158 thousandths. But we want to go another 29 thousandths, so we're going to add 29, and that's where we're going to take our two finish cuts, 187. Now, I'm not going to take that entire 29 thousandths cut in one go because it's a little bit big for a finish cut, okay? So I'm going to go to 180 thousandths, take two cuts, and then I'm going to go to the 187 and take a finish cut of 7 thousandths off of both sides. Try to clear these chips when you can, because these end mills really don't like to recut chips. You can very easily damage them. Okay, final cuts now, and believe it or not, I'm going to take this as a climb milling pass because it'll give me a little bit better surface finish. So now I'm at my full 187. Here we go. This is such a small cut that we really don't need to worry about this whole bouncing around inside of the lead screw business. Okay, 187 in the other direction. Let's go. Absolutely gorgeous. Okay, go ahead and put the adjustable parallel in there and open it up. Let's go in there with the outside micrometer and measure over top of the parallel. Okay, let's see what we've got. It says 850 plus 22 and a little change. So 850 plus 22, 872 and a little bit. The target was 875 plus or minus 5, so we're definitely inside of that range. Now let me check the tab widths just to make sure that we're still on center. 502 thousandths right there. And just under 502 thousandths right there. So they agree within a little bit less than a half a thousandths, and we're about 3 thousandths smaller than our target size for the slot width. So this is good to go. Okay, let's go ahead and clean all this stuff off. Okay, I'm going to go ahead and take this thing out because actually that's all we're going to do in this demonstration video. And I really want to get all of these burrs off of all of these square edges. In the next video, we're going to go ahead and put in all of these holes. And we're going to start with this big bore right here. So actually, we're going to have to change out the parallels anyway. So now's a good time to take this thing out. So deburr all of the edges. This is going to be a lot easier for me to do off screen. You know, getting into those little nooks and crannies with a big file is kind of challenging. So I grabbed one of these small files. It's called a jeweler's file, but it's basically like a miniaturized version of a mill file. We have a canister filled with random kinds of files in very small sizes that you can use for getting into specialty features and shapes and tight corners and such. Some of them are just miniaturized versions of files that we often see. Some of them have these kind of odd shapes, and they belong to a family of files called Riffler files, made to get into very tight corners and strange places. So, you know, if you need one, you know where to find them. Well, folks, that's all we're going to do in this video, the second part of the demonstration for the NIMS Step Block. We finished all of the planar surfaces, and now all we need to do is go in and put the holes into the top surfaces and bore this big one out. But that's going to be part 3. I'll see you then. Bye.